Welcome to the deep dive. Get ready to go deep because today we are cracking open a fundamental text in the world of surgery. We're talking about the essential principles of surgical audit and research the kind of foundational knowledge that truly distinguishes, well, the elite professionals in the field.
That's right. We're pulling from a key chapter in a standard surgical textbook. And our goal isn't just to skim the surface. We're here to really unpack the core concepts, understand the crucial why and how behind evaluating and innovating in surgery, and, equip you with the mindset and knowledge to master this space.
Because surgical practice isn't static, is it? Surgeons are constantly evaluating their own performance, assessing new techniques, adopting new technologies. This material makes it clear that involvement in audit and research isn't optional for a successful career. It's a cornerstone.
Absolutely.
Right.
And it's not just about doing your own work. With the explosion of surgical literature, understanding these principles is the only way you can critically appraise the work of others. You really need to know how good research is done to spot weak research when you see it.
Right, you need that critical filter. So consider this your shortcut to being truly well-informed and mastering these critical skills. Let's jump in. The very first thing this material tackles is a fundamental question you have to ask right at the beginning of any project. Is this audit or is it research?
That distinction is absolutely critical, and here's why. It dictates the entire framework you'll operate under, from approvals all the way to how you report your findings.
Okay, unpack that a bit. What's the core difference? What really separates the two?
Think of it this way. Audit is primarily about quality assurance. Health professionals are expected to undertake audit or service evaluation to improve care based on existing standards or guidelines. You're measuring your current practice against what's already accepted as good practice.
So checking if you're meeting known benchmarks, like a performance check.
Exactly. Measuring against the known standard. Research, on the other hand, is specifically designed to generate new knowledge. You're testing something novel, maybe a new treatment, a new surgical approach that isn't yet accepted standard care. You're trying to find out if something should become the standard.
Ah, okay. Innovation versus evaluation against the known. That clarifies it. How does the source suggest figuring this out formally? Is there a tool or something?
It points to a helpful tool, like the UK Health Research Authority, or HRA decision tool. It basically poses three key questions to guide you. First, are participants randomized? Randomization is a hallmark of testing something new, comparing interventions.
Right, randomization screams research, usually.
Usually, yes. Second, does the study protocol require changing treatment or care from accepted standards for any patients involved? If you're intentionally doing something different from the norm as part of the study, it's likely research.
Okay, those first two seem like pretty clear signposts pointing towards research. What's the third question? That one sounded a bit trickier.
Third, is your study designed to produce generalizable or transferable findings?
That's the one. Yeah, the source mentions that can be tricky. What do generalizable and transferable really mean in this specific context?
Good point. The HRA defines these quite carefully. Generalizable means the findings can be reliably extrapolated from your specific study population to a broader population, or maybe applied to settings different from where you actually did the study.
Mm-hmm.
Think results that could potentially change practice everywhere.
Okay, so widely applicable findings. Got it.
Right. Transferable, which is typically used more for qualitative studies, means the findings can be applied to a similar context or setting. Now, here's the key insight from the source on this. Most audits are actually considered hypothesis generating.
Hypothesis generating. Meaning?
Meaning they might reveal something important about your specific hospital's performance, perhaps suggesting an idea for improvement. But you would generally need a separate prospective research study designed specifically for generalizability to prove that idea holds true more broadly. Audits usually don't meet that high bar for generalizability in the HRA sense.
I see. So an audit might flag up something interesting in your local practice, give you a hypothesis, a starting point, but you need proper research to confirm if that finding is relevant and truly applicable elsewhere.
Exactly. The audit identifies a potential issue or an interesting pattern. The research study is designed to confirm its significance and wider applicability. Getting this right up front is crucial because it determines your regulatory path, your ethical review needs, and even how you should really analyze and report your data.
Understanding that initial fork in the road seems absolutely vital then. Let's focus specifically on audit and service evaluation for a moment. What's the formal process look like?
Okay, so clinical audit is formally defined as a process clinicians use to improve patient care. And it works by comparing aspects of care, Things like the facilities you have, that's the structure, or how you actually do things, the process, or critically, what happens to the patient, the outcome, comparing all that against explicit criteria and defined standards.
This feels like something surgeons should be doing almost constantly as part of reflective practice.
It absolutely is,
Yeah.
or it should be. It's really about continuous monitoring. Surgeons routinely keep track of their own outcome data, often contributing to clinical databases. This lets them monitor their individual performance against agreed standards and, critically, compare it to national data sets to see how they stack up.
Which, for surgeons in the UK, is a key part of things like revalidation, right? They have to show they're doing this.
Precisely. It's an essential professional responsibility. And the real power of audit isn't just the measurement, it's the action that follows. If the comparison shows that care falls short of the agreed standard, the audit process requires you to propose changes.
What kind of changes are we talking about? Can audit really drive significant change, or is it more minor tweaks?
Oh, absolutely, it can drive change. The source highlights that findings from audit can lead to changes at many different levels. It could be something quite personal, like identifying a need for individual training or perhaps better equipment for a specific procedure.
Okay, individual level.
Or it might be a team issue that needs addressing, or even require a bigger institutional change, like implementing a whole new hospital-wide antibiotic policy based on resistance patterns found in an audit.
Wow, okay, so bigger system changes too.
Definitely. And sometimes the findings are so significant they point to a need for changes at a regional level, perhaps consolidating complex cases in specialized tertiary centers or even nationally, potentially leading to new screening programs or updates to national guidelines.
So audit isn't just checking boxes. It can be a really powerful driver for system-wide improvement, all starting from that basic process of evaluating performance against a known standard.
That's the key insight. The source also makes a distinction between local single-site audits and larger multi-site audits. These could be regional, national, or even international collaborations. Often, a local audit identifies a concern right there at the coalface, and that finding might then trigger a bigger multi-site audit to see if it's actually a widespread issue across many hospitals.
And where do these local audit questions often bubble up from? What sparks them?
Very frequently, they come up in those crucial departmental morbidity and mortality or M&M meetings. A case discussion that highlights a potential problem or an unexpected outcome might spark the idea for a formal local audit, which then, as I said, could potentially scale up.
Okay, this brings us neatly to the formal structure, the audit cycle. It sounds quite methodical. Walk me through the essential steps.
The audit cycle is a structured process designed to ensure effectiveness. It typically has 7 key steps. First, you define your audit question. What specific aspect of care are you actually looking at? And ideally, this is done with input from the whole multidisciplinary team.
Get everyone involved from the start. Makes sense. Step 2.
Second, you identify the relevant evidence base and the existing standards you'll compare against. You need to know what good looks like according to current best practice or guidelines.
So establish your benchmark first. Got it.
Exactly. Third, you design the audit itself. How will you measure performance against those standards? What data do you need? This step often involves seeking advice, maybe from an audit department, and certainly getting institutional agreement to proceed.
Plan the measurement. Then.
Fourth, you measure over an agreed interval. You actually go out and collect your data systematically according to your plan. Fifth, you analyze the results and compare your measured performance against those predefined standards.
And that comparison leads to the gap analysis part, right? Seeing where you fall short.
Yes, step 6 is undertaking that gap analysis. If you find you met or even exceeded the standards, great. You typically plan to re-audit later, maybe in a year or two, just to ensure standards are maintained. But if there's a shortfall, if you're not meeting the standard, you need to identify and agree on interventions needed for improvement. That might involve training, process changes, new equipment, whatever is needed. And you agree this with everyone involved.
Okay. Identify the problem, figure out a solution. And the crucial final step must be?
Step 7, re-audit. You have to close the loop, you implement the changes you agreed upon, give them time to bed in, and then you measure again using the same methods to see if your performance has actually improved and now meets the standard.
Measure, compare, act, measure again. It really is a continuous quality improvement loop. Now, the source mentions a newer type of audit that's gaining traction, the multi-center snapshot audit. Sounds really interesting.
It's a really exciting development, yeah, especially in surgery, and it's been pioneered largely by these trainee collaborative groups we'll talk more about later. It involves a large number of collaborators across many different hospitals, prospectively, collecting anonymized patient data on a specific topic. But, and this is key, only for a very short, defined period, typically just 6 to 8 weeks.
Wow, that is a short time frame. What's the power of this rapid, wide approach?
It allows researchers to quickly gather large amounts of contemporaneous real-world data from a very diverse patient cohort across many settings. The main purpose isn't usually to prove something definitive, but rather to explore differences in patient characteristics, in the surgical techniques being used, or in management strategies across many sites simultaneously.
And the outcome isn't necessarily a final answer then, it's more exploratory.
No, that's the key insight, exactly. The primary outcome is usually generating hypotheses. These snapshot audits are fantastic at identifying areas of significant practice variability between hospitals or highlighting apparent outcome differences that really warrant further, more rigorous prospective research. They essentially reveal where the important research questions might lie.
Ah, I see. So it's a really rapid way to survey the landscape and spot the areas that need deeper investigation through formal research. What are the main advantages? Why do people like this approach?
The source lists several key benefits. First, they are highly accessible. They can often be conducted at almost zero direct cost to the individual researcher or trainee, which is obviously fantastic for people starting out or without major funding.
Low barrier entry. Good.
Yeah. They are also excellent for bringing new groups of people together and fostering collaboration across different hospitals or regions. And critically, they generate high-quality contemporaneous data on actual, real-world clinical practice, not just what happens in a highly controlled trial setting.
That scalability, speed, and real-world relevance are powerful. And it leads us perfectly into the next section, identifying a research topic, which is designed to generate that new knowledge we talked about earlier.
Right. Now we're moving from evaluating what we currently do, using audit, to discovering something genuinely novel through research. So how does a surgeon identify a good research question? It often starts with an observation, maybe a puzzle or a nagging question from their daily clinical practice. That initial idea then needs to be transformed into a clear, testable hypothesis.
And where do you get help refining that idea?
The source suggests talking to experienced, published surgeons in your field. They often have a really deep understanding of where the significant gaps in knowledge currently are, where the controversies lie, what questions really need answers.
I imagine refining that initial idea, honing the question, is absolutely critical. You don't want to pursue a dead end.
It's probably the single most important step in the entire research process, according to the source material. You must spend quality time refining your question. The crucial question you have to keep asking yourself is, does this question really matter? Is the potential answer genuinely important for patient care or for advancing surgical knowledge? Choosing the wrong topic, even if you execute the study perfectly, means countless wasted hours if the fundamental question wasn't really worth answering in the first place.
That's a harsh, but I suppose necessary truth in research. And I guess you can't just dive straight into collecting data once you think you have a good question.
Absolutely not, no. Before you even think about collecting a single piece of data, you must do your homework. You have to find out if someone else has already comprehensively answered your question. And equally important, you need to check if the methodology you're planning is actually appropriate and robust enough to answer it convincingly. Finding out at the very end that your study is redundant because it's already been done, or fundamentally flawed in its design, is, as the source rather bluntly puts it, the worst possible outcome.
Ouch. Okay, so a thorough, comprehensive literature search is completely non-negotiable. Where should you be looking?
Well, first port of call is usually the internet, searching the major medical databases like PubMed, Embase, and so on. But the source strongly advises getting help from a medical librarian. They are absolute experts in navigating the vast sea of published literature efficiently and accurately. It's not enough just to skim abstracts. You need to really dig into the details of prior studies to understand what was done and what wasn't. They specifically mention the Cochrane collaboration as an invaluable resource for finding high-quality, systematic reviews of existing evidence.
Cochrane is definitely a go-to for evidence synthesis. Are there other good sources of inspiration for finding impactful research questions?
Yes, and these are really great places to look, actually. High-quality national guidelines, like those produced by NICE, the National Institute for Health and Care Excellence in the UK, often have a specific section titled Recommendations for Research.
Really? They actually list the gaps.
They literally list the questions, where the expert guideline panels reviewed all the available evidence and found it was insufficient, lacking, or conflicting. They're basically telling you directly, Here are the important knowledge gaps that need filling.
That's incredible. It's like a ready-made list of high-priority research topics.
Exactly. Designing a project around one of these points makes it inherently important and often much easier to justify when you're applying for funding or seeking ethical approval. Another fantastic source the text mentions is Priority Setting Partnerships, or PSPs. Organizations like the James Lind Alliance facilitate these.
What do they do?
They bring together patients, carers, and healthcare professionals to jointly identify and prioritize the top research questions they collectively believe are most important and need answering.
So research priorities driven directly by the people who are most affected by the condition or treatment, that seems incredibly powerful and relevant.
It really is. Projects that address these patient and clinician-identified priorities are often very well received by funders and review panels, and sometimes they're even specifically prioritized for funding calls. Finally, the source also mentions seeking support from dedicated networks like the NIHR Research Design Service in the UK.
What do they offer?
They offer free, expert, confidential advice on all aspects of study design, methodology, statistics, finding funding, patient and public engagement with the works. They often run training courses too. They can really help you refine your question and develop a robust plan to answer it.
That level of dedicated support sounds invaluable, especially for trainees or surgeons navigating the research world for the first time.
It truly is a fantastic resource. And once you have that solid question, you've done your background literature search, the next absolute crucial step the source emphasizes is forming a team.
Why is having a team so vital? Can't a single, really dedicated surgeon just push a project through?
The source is quite emphatic about this. Failing to involve others is one of the most common reasons for the failure of an otherwise good research project. It states that very few meaningful studies can realistically be completed by a single person working entirely alone. Almost any project worth doing, it says, will need a team to deliver it.
Is that mainly because of the sheer amount of work involved in most research?
That's definitely a major part of it, yes. But it's also about bringing together diverse skills and experience. And perhaps most importantly, it's about maintaining momentum. Research projects invariably take time, often years, and life happens. People have exams, family emergencies come up, clinical work gets incredibly busy. A team ensures that when one person inevitably has to step back for a period, others can keep the project moving forward. It prevents individual burnout and ensures the project has the longevity to reach completion.
That makes perfect sense. Shared load, shared expertise keeps things going. So how do you actually form a team? What are the options?
Well, you can certainly build one locally. You might team up with interested colleagues, junior doctors, nurses, allied health professionals, and find an experienced local mentor to guide the project. Or, and this is an area where surgery has really led the way globally, you can join an existing collaborative research group.
Ah, yes, the collaboratives. Tell me more about these. The source highlights the UK's West Midlands Research Collaborative, the WMRC, as a pioneer.
Yes, the WMRC was founded back in 2008. It was started by surgical trainees who were, frankly, frustrated by how difficult it was to conduct high-quality research alongside their demanding training schedules and frequent hospital rotations. The premise was simple, but quite revolutionary at the time. Pool resources and collect data simultaneously across all the different hospitals where the members were rotating through during their training.
So they actually leveraged the trainee rotation pattern, which is usually seen as a barrier to research continuity?
Exactly. Trainees move between hospitals, but the collaborative network itself and the research projects being run within it remain rooted and ongoing. This structure provides project longevity that individual trainees couldn't achieve alone. And crucially, it creates a critical mass of engaged individuals across multiple sites, which generates and maintains the momentum needed to drive large studies forward.
That's clever. What kind of studies do these collaboratives particularly excel at?
They are especially effective for conducting relatively simple, pragmatic randomized controlled trials, or RCTs, and also those large multi-center snapshot audits we discussed earlier. Because they have members spread across many hospitals, they can recruit patients much faster, and for more diverse settings than any single center could ever manage alone.
The source uses the Rossini trial as a prime example of this model in action.
That's right. The Rossini trial was the WMRC's first major RCT. It tested a simple, inexpensive intervention, a wound edge protection device to see if it reduced surgical site infections after abdominal surgery. By mobilizing trainees and consultants across 21 different hospitals, they managed to randomize over 760 patients and completed the entire trial ahead of schedule.
Wow, 760 patients across 21 sites finished early. That is incredibly efficient and really demonstrates the power of that collaborative model.
It absolutely galvanized the whole movement. That success story really showed what was possible. Now, the source notes there are trainee-led general surgical collaboratives in basically every region of the UK. There are national specialty collaboratives in areas like urology, plastics, orthopedics. There are international collaborative groups in many countries with similar training structures. And the model has even spread successfully to medical students with networks like StarSurg and into other non-surgical specialties as well.
It's become a genuine global phenomenon in medical research. What's the core principle that makes them work so well, do you think?
The source stresses one thing above all: complete inclusivity. Anyone who is interested in contributing to research, whether they're a medical student just starting out, a trainee in the middle of their program, or a senior consultant surgeon, is welcome to join these groups, get involved in existing projects, or even propose new ideas. It's a very open and democratic structure.
That sounds like a fantastic entry point into surgical research for anyone interested, and a really effective way to contribute meaningfully to the field.
It really is. Okay, so once you have your research question refined and your team is in place, whether local or collaborative, the next major phase is meticulous project design.
Right. This is where you map out exactly how this study will actually work in practice.
Precisely. And the source absolutely cannot stress this enough. Time spent carefully designing a potential project is never wasted. It might feel slow at the beginning, but getting the design right up front saves huge amounts of time and potential heartbreak later. Before you start thinking about collecting any data, you must sit down and answer some really critical questions about your proposed study.
Like the ones outlined in that summary box 13.1 in the text.
Yes, those are essentially your design checklist. You need to ask, why are we actually doing this study? Is the question genuinely useful and important? Is the project practical and achievable with the time, money, and resources we actually have available? Would it benefit from collaboration, maybe joining forces with another group? What are our expected findings, realistically? What are the governance requirements we'll need to meet? What are the ethical issues we need to consider and address? And ultimately, what potential impact could our results actually have on practice or future research? Thinking through all of these systematically upfront prevents major problems down the line.
That level of thoroughness seems absolutely essential to avoid wasted effort. The source also then goes on to describe different types of study designs that you might choose.
Yeah, there's a whole spectrum of designs. Broadly speaking, you can divide them into observational studies, where you essentially observe what happens to a defined population without intervening beyond standard care, and experimental studies, where the researcher actively intervenes and controls the allocation of participants to different groups, like assigning them to receive a new drug or a standard one.
And observational studies themselves can be retrospective, looking back at data that already exists, or prospective, where you plan ahead and collect new data specifically for the study as it happens.
Correct. And within those broad categories, you have specific designs, each suited to different types of questions. There are case control studies, cross-sectional studies, longitudinal or cohort studies, randomized studies, and of course the design often considered the gold standard for testing interventions, the randomized controlled trial, or RCT.
Why are RCTs generally considered the best design for testing treatments?
Primarily because the process of randomization, randomly assigning participants to different groups, helps to balance both known and unknown characteristics between those groups. This reduces the risk of bias and increases our confidence that any difference we observe in the outcomes between the groups is actually due to the intervention being tested, rather than some other underlying difference between the patients themselves.
So it helps isolate the effect of the intervention.
Exactly. However, the source makes a really crucial point here. Much of surgical innovation doesn't, and perhaps can't, start with a full-scale RCT. If you're developing a completely new operation, for instance, you first need to establish if it's feasible, if it's safe in a small number of patients. That requires initial feasibility studies or pilot studies. The source specifically mentions guidance from groups like the Ideal Collaborators for how to introduce and evaluate innovative surgical techniques ethically and effectively through a staged process, often starting small before scaling up to an RCT if appropriate.
So picking the right study design depends entirely on the specific question you're asking and also the stage of development of the intervention you're evaluating. It's not always RCT or nothing.
Absolutely. You absolutely need the right tool for the right job. The source also makes an important distinction between qualitative and quantitative research approaches.
Right. What's the core difference there? What are we measuring?
Okay, so quantitative research deals primarily with numbers, objective endpoints that you can measure and count. Things like mortality rates, complication rates, perhaps using standardized systems like the Clavian-Dindo classification to grade severity or length of hospital stay, tumor size, blood pressure readings. You analyze this numerical data using statistical methods.
Hard, measurable facts and figures.
Yes. Qualitative research, on the other hand, explores experiences, perspectives, beliefs, and meanings. The data often comes from things like patient interviews, focus group discussions, or observational notes. It looks at the psychosocial impact of a condition or treatment, or uses quality-of-life questionnaires to capture subjective experiences.
So it's more about the numbers versus the human experience and context.
Exactly. And the source notes that actually much of the best research is both quantitative and qualitative, integrating both approaches. Combining objective measures like survival rates with subjective patient experiences can provide a much richer and more complete understanding. They particularly highlight the increasing importance and use of patient-reported outcome measures, or PROMs.
Proms. Tell me more.
These are tools or questionnaires designed to capture outcomes directly from the patient's perspective, how they feel, how well they are functioning in their daily lives, their symptoms, their overall quality of life. This is incredibly valuable because it shifts the focus beyond just clinical metrics to what actually matters most to the patient themselves.
That makes perfect sense. Ultimately, the patient's experience and functional outcome are key goals of surgery. The source also mentions focusing research according to strategy. What does that mean?
Yeah, it suggests that aligning your research project with existing institutional, national, or perhaps even international strategic priorities can increase its relevance and potentially its likelihood of receiving support or funding. And, given the financial realities of modern healthcare systems, the source points out that major research projects, especially those proposing new and potentially expensive interventions, often need to include a formal cost-benefit analysis to demonstrate the economic value of the proposed change. Frameworks like the NIHR guidance in the UK help with this.
Okay, so design is clearly a complex, multifaceted process involving the question, the team, the methods, the outcomes. And a crucial part of that design, especially for quantitative studies aiming for those generalizable findings, is calculating the sample size.
Oh, absolutely critical. Calculating how many patients you actually need for your study is fundamental, and the source pulls no punches here, calling an incorrect sample size probably the most frequent reason for research being invalid. Surgical trials, perhaps because interventions can be complex and effect sizes variable, seem particularly prone to this issue of being underpowered.
Why is it so easy to get wrong, and why does having the wrong sample size completely invalidate the study?
It really boils down to statistical power and the risk of making incorrect conclusions. There are two main types of errors you're trying to avoid when you calculate your sample size: type I and type 2 errors.
Okay, break those down for me. Type I.
A type I error is essentially a false positive. It's when you conclude that your intervention works or that there's a significant difference between your groups, when in reality the difference you observed was just due to random chance or variability. You're claiming a benefit or difference that isn't truly there in the wider population.
Okay, finding something that isn't real. What about type 2?
A type 2 error is the opposite. It's a false negative. This happens when there is a real benefit or difference associated with your intervention, but your study was too small, it lacked sufficient statistical power to detect it reliably. You missed a real effect because your magnifying glass wasn't strong enough to see it against the background noise of random variation.
Ah, okay. So sample size calculation is all about ensuring you have enough power, enough patience to confidently detect a real effect of a certain minimum size, if it actually exists, while also minimizing the risk of being fooled by random chance.
Precisely. The calculation essentially tells you how many participants you need in your study to be reasonably confident. Typically, researchers aim for 80% or 90% power of detecting a clinically meaningful difference between your groups, assuming that difference truly exists, while keeping the chance of a false positive result low, usually set at less than 5%, the p.05 significance level.
And the source makes the point that often when you do this calculation properly, the number you need turns out to be more patients than are readily available at a single hospital or center.
Exactly. Which is precisely why multi-center studies, often run through those collaboratives we discussed, are so frequently necessary for robust clinical trials. Recruiting from multiple sites not only helps achieve the required sample size faster, but it also has the added significant benefit of improving the external validity or generalizability of your findings because you're recruiting from a more diverse population across different settings.
That makes sense. And you also have to factor in that not everyone who starts the study will finish it, right? You have to account for patients dropping out or being lost to follow-up.
Absolutely. That's the attrition rate. You always need to plan for this and recruit or randomize more patients than your final target sample size calculation indicates to account for this inevitable loss over time. The longer your planned follow-up period for the study, generally the higher the attrition rate you need to anticipate and build into your recruitment target.
The source walked through a sample size calculation example, something about reducing a complication rate from 30% down to 20%. Can you simplify the intuition behind how that works?
Okay, let's take that example. Imagine the standard complication rate for a procedure is 30%. You have a new technique you think might be better. You decide, perhaps based on clinical judgment or previous pilot data, that a reduction down to 20%. So a 10% absolute reduction would be a clinically meaningful improvement worth adopting. The sample size calculation takes that desired effect size, the 10% difference, the baseline rate 30%, your desired level of confidence in detecting it if it's real, say 90% power, and your acceptable risk of a false positive, say p.05 significance. And it crunches the numbers to tell you how many patients you would need each group, the new technique group and the standard care group, to reliably detect that 10% difference if it truly exists. In the example given in the text, it comes out as needing 333 patients per group.
Wow, so 666 patients total, and that's before you even factor in extra numbers to cover potential dropouts. That really highlights why these numbers can get big very quickly, and why pooling patients through collaboratives is often the only feasible way to answer important surgical questions with adequate power.
Exactly. It puts the need for collaboration into sharp focus. Now, alongside sample size, another absolutely critical design element is thinking about and actively trying to eliminate potential bias in your study. You have to constantly ask yourself, what factors, other than the intervention itself, could unfairly influence the results we observe?
And how do you actively try to mitigate that bias? What are the main techniques?
A key technique, particularly in experimental studies like RCTs, is blinding or masking. This means trying to keep the people involved in the study unaware of which treatment group a particular participant has been assigned to. There are different levels. You can have a blinded observer or assessor. The person collecting the outcome data doesn't know the patient's group assignment.
Okay, blinding the data collector.
You can have a single blind study where the patient is unaware of which treatment they're receiving, though the researchers might know. But the gold standard, wherever it's possible and ethical to implement, is a double-blind study. In this case, neither the patient nor the researchers interacting with them or assessing their outcomes knows the treatment allocation until the entire study is completed and the code is broken.
Double-blind sounds ideal for minimizing bias, but I imagine in many surgical trials that's just not practically possible or even ethical. You can't really blind the surgeon to which operation they are performing.
That's a very crucial point the source makes explicitly. It's often impossible to blind the surgeon doing the operation, and sometimes blinding the patient isn't feasible or ethical either, especially if the interventions look or feel very different. The key is to implement blinding wherever you realistically can. Perhaps blinding the pathologist reading specimens, or the radiologist interpreting scans, or the independent assessors who evaluate functional outcomes, even if the patient and surgeon themselves aren't blinded to the core intervention. And you must be completely transparent in your reporting about who was blinded and who wasn't and why.
Be honest about the limitations. Okay, so once you've wrestled with your question, assembled your team, thought through the design principles like study type, outcomes, sample size, and bias mitigation, you need to document all of this meticulously in a formal study protocol.
Yes, the protocol is essentially your detailed master blueprint for the entire research project. It's created after the core research question has been finalized and the sample size has been properly estimated.
What absolutely essential information must that protocol contain? What are the key ingredients?
It really needs to contain everything another researcher would need to fully understand, critique, and potentially even replicate your study. That includes a clear background section explaining the rationale, precisely stated aims and objectives, a very detailed methodology section covering the study design, the patient population definition, clear inclusion and exclusion criteria, the interventions being compared, the primary and secondary outcome measures, and a sample size justification, plus your proposed statistical analysis methods, the target patient numbers, and the overall projected timeline for the study.
So detailed enough that, in theory, another independent team could pick up your protocol and run the exact same study.
That's the ultimate goal, yes. It needs that level of clarity and detail. The force suggests that constructing a simple flow diagram can be a really helpful way to provide a clear visual summary of the protocol. It points to figure 13.1 in the text, which shows the protocol summary for the Sunrise trial as an excellent example. That diagram concisely presents the key elements: the research topic, the study design, RCT, the number of participating centers, the inclusion and exclusion criteria, the total number of patients needed, expected attrition rates, the randomization ratio, and the core details of the sample size calculation.
Visualizing the patient flow through the study like that seems very useful for clarity. The source also gives a great practical tip related to protocols. Try to imagine writing the final paper before you even start collecting data. How does that help?
Yes, that's a simple but surprisingly powerful exercise. By trying to draft your planned results tables and figures, and thinking about exactly what information you'll need to report in the methods section and what points you want to make in the discussion, you can often preemptively identify crucial pieces of data you might otherwise forget to collect, or potential ambiguities or weaknesses in your plan design or analysis. It really helps to stress test and refine the protocol before you commit to it.
That's smart. Foresight prevents problems.
Right.
So careful design leads to a strong protocol. What about the practicalities of actually running the study? Things like securing funding, managing time, handling the data, using technology, and getting the study registered.
These are the crucial logistical hurdles you absolutely must plan for right from the outset. The source emphasizes the need to allocate sufficient time early on for critical, often time-consuming steps like fundraising, because research, unfortunately, isn't free, and obtaining all the necessary approvals. That includes ethical approval, regulatory approvals if needed, and institutional approvals like HRA approval in the UK system. These processes can take many months.
And you need to factor in budget and time not just for the active data collection phase, but also for the subsequent data analysis and the writing up process too.
Absolutely. And that time, including staff time for analysis and writing, needs to be properly costed into any grant applications you submit. You also need to carefully identify and budget for any non-routine investigations or extra treatments that are required purely because of the research study protocol. These costs should typically be covered by specific research grants, following established guidance like the UK's ACORD framework, rather than falling on standard healthcare budgets.
Data management sounds like it could be a huge undertaking, especially for large multi-center studies. What's involved there?
It is a major task, yes. You need to design clear, unambiguous data collection forms, or, more commonly now, set up a secure, reliable computer database for electronic data capture. The source stresses the absolutely paramount importance of having robust systems in place to safeguard patient privacy and confidentiality, and also to ensure the quality and integrity of the data being collected, all in compliance with relevant legislation like GDPR.
Data security, confidentiality, and accuracy are completely non-negotiable.
Precisely. You need things like validation rules built into electronic databases to catch errors at the point of entry. You need clear plans for secure, long-term data archiving after the study finishes, often in institutional or national repositories like the UK Data Archive, especially if funders require open access to data. And you need robust quality assurance processes during data collection, things like training the staff who will be entering the data, having clear standard operating procedures, SOPs, for every step, and periodically monitoring or checking samples of the data for accuracy and completeness. At the end of the study, the final analysis database must be meticulously cleaned, checked, and then formally locked to prevent further changes. Safe storage during the study and a clear archiving policy afterwards with a nominated data custodian are essential.
How has technology changed the game here, especially for facilitating those large collaborative studies spanning multiple sites, maybe even countries?
Technology has fundamentally transformed collaborative research. Things like secure online communication platforms and validated electronic data capture, EDC databases. The source mentions RADCap as a popular example, which was used successfully in the Sunrise trial across both the UK and Australia, allow research teams to work together seamlessly in real time, regardless of their physical location. They enable secure data entry, automated randomization processes, progress monitoring, and communication across national and international groups, facilitating studies on a scale and speed that would have been completely impossible just a couple of decades ago.
So it really enables that large-scale, efficient, collaborative work we were discussing earlier. What about study registration? Why is that important?
This is now a mandatory requirement for many leading medical journals before they will even consider publishing the results of a clinical trial. The idea is that you register your study protocol outlining your key design features, outcomes, and analysis plan on a publicly accessible online database such as ISRCTN or clinicaltrials.gov before you recruit your very first participant into the study.
And what's the main purpose of doing that public registration up front?
Primarily, transparency and accountability. It makes the existence and design of ongoing trials publicly known, which helps researchers see what else is happening in their field, potentially reducing unnecessary duplication of effort. Perhaps more importantly, it helps combat publication bias, the tendency for studies with positive or statistically significant results to be published more readily than those with negative or inconclusive findings. By registering upfront, there's a public record of the trial existing, regardless of its eventual outcome. You also need to keep the registry entry updated throughout the study, and importantly, upload your summary results in a timely manner once the study is complete. The source notes this whole registration process can sometimes be complicated, so getting institutional support is advisable. But the bottom line is, major journals simply won't publish an unregistered clinical trial these days.
It forces transparency and helps ensure all results, positive or negative, eventually see the light of day.
Okay, so we've covered design, protocol, practicalities. Next up are the vital layers of regulatory and ethical frameworks that govern research.
Yes, this is absolutely non-negotiable for conducting research responsibly, ensuring patient safety, and maintaining public trust. Formal frameworks exist. The source uses the UK Policy Framework for Health and Social Care Research as an example to enhance the integrity of research and ensure all necessary requirements are met. A key concept within these frameworks is that of sponsorship.
What exactly does sponsorship mean in the research context? It's not just about funding, is it?
Yeah.
No, not necessarily just funding, although the sponsor might also be the funder. The source, referencing the HRA definition, explains that the sponsor is the specific organization, typically a university, an NHS trust or hospital, or sometimes a commercial company that takes ultimate responsibility for the initiation, management, and overall conduct of the research project. They are primarily responsible for ensuring appropriate standards of design, conduct, and reporting are met, and that all legal and ethical requirements are adhered to.
So it's the institution or entity that formally stands behind the research and is accountable for it being done properly.
Exactly. This overarching sponsorship framework helps ensure that crucial processes like independent peer review, ethical review, data protection, pharmacovigilance, if applicable, and financial oversight are all properly managed according to established standards.
You mentioned peer review there. How does that fit in?
Formal, independent peer review of your finalized study protocol is an essential step. Before you submit for ethical or regulatory approvals, your protocol should ideally be reviewed by other experts in the field who are independent of the study team. In the UK, evidence of this peer review is actually required for ethics and HRA applications. Funders, naturally, also conduct their own rigorous peer review as part of the grant application process. This feedback process, while sometimes challenging, is incredibly valuable. External reviewers can often identify potential flaws, weaknesses, or areas for improvement in your design that you might have missed.
Get expert eyes on it before you commit. An ethics review obviously crucial, but beyond just using common sense, independent committee review is needed.
Absolutely. Common sense and adhering to basic ethical principles are the starting point, of course. But formal, independent ethics committee review is mandatory for almost all research involving human participants, their tissues, or their data, especially patients or carers within a healthcare system. In the UK, the NHS Research Ethics Committees, NHS RECs, provide this crucial independent scrutiny for studies involving the NHS. There are integrated application systems, like IRS, the Integrated Research Application System, designed to streamline the process of applying for ethical and other regulatory approvals simultaneously.
What if your study doesn't strictly fall under the remit requiring NHS REC review? Maybe it's using anonymized data or involves only healthy volunteers outside the NHS.
Even in those cases, the source strongly advises that you should still seek independent ethical review, often through your own institution's internal research ethics committee. Most universities and many hospitals have them. For collaborative projects involving multiple sites, the principle is usually to get lead ethical approval from one REC, with local sites then accepting that review, avoiding unnecessary duplication of effort. The source also makes the practical point that correctly filling out the detailed ethics application forms, while sometimes seeming bureaucratic and time-consuming, actually serves a valuable purpose. It forces the investigators to think through all the practical and ethical aspects of their study in detail, which ultimately prepares them well for conducting it responsibly.
And when dealing with the ethics committees themselves,
Intelligence and courtesy are key, the source wisely notes. If you're invited to attend the ethics committee meeting where your application is being discussed, it's highly recommended that you go. It allows you to answer questions directly, clarify any points of confusion, and often resolve potential issues much more efficiently than through written correspondence. Maintain a professional and respectful dialogue.
Good advice. What about other regulatory approvals beyond ethics? Are there other bodies involved?
Yes, depending on the type of study. Interventional clinical trials involving new medicines or medical devices are subject to specific, strict regulations. In the UK, the key regulatory body for this is the MHRA, the Medicines and Healthcare Products Regulatory Agency. For studies involving NHS patients, their data, or NHS facilities in England and Wales, formal HRA approval is required, which integrates ethical review with other governance checks. Participating NHS sites also need to confirm they have the local capacity and capability to actually run the studies safely and effectively. And research involving animals is also tightly regulated, requiring specific Home Office licenses in the UK and adherence to reporting guidelines like the ARRIVE guidelines to ensure transparency and rigor.
So quite a significant landscape of different approvals to navigate, depending on exactly what your study involves.
It can be complex, yes, which is another reason why having good institutional support, experienced collaborators, and potentially accessing resources like the Research Design Service is so vital, especially for less experienced researchers. And underpinning this whole regulatory and ethical structure is the fundamental principle of research integrity.
The source mentions frameworks like the Concordat to support research integrity in the UK. What's the essence of that?
These frameworks, which have equivalents internationally, set out the fundamental principles and commitments expected for conducting research honestly, rigorously, and transparently. Key commitments typically include honesty in all aspects of research, including reporting results accurately, rigor in methodology and analysis, accountability and transparency throughout the research process, professional courtesy and fairness in working with others, and good stewardship of research resources, including data and funding.
Simple principles, really, but absolutely foundational to trustworthy research.
Completely non-negotiable. And the single most crucial rule the source emphasizes coming out of this whole section is this: you should never start participant recruitment for a study until all the appropriate ethical and regulatory approvals have been formally granted, and you are confident that your study adheres to the principles of research integrity. Trying to get retrospective approval is usually impossible and unethical. The source also notes that international resources, like the NIH's ClinRegs website, exist to help researchers navigate the specific requirements in different countries.
That's a massive amount of essential groundwork to lay before you even collect the first piece of data. Once you do get your data, you then face what many consider another major challenge: the statistical analysis.
Ah yes, statistical analysis, often cited as the most daunting part for many clinicians who aren't trained statisticians. And, according to the source material, it's also the part of published clinical papers that is most frequently, and often justifiably, criticized for being inadequate or inappropriate.
So what's the single strongest piece of advice the source gives here?
Get expert statistical help, and crucially, get it early in the process. The source strongly advises consulting a qualified statistician before you even finalize your study design and protocol, not just showing up with a pile of data at the very end and asking them to do the stats.
Why is involving them so early that important? Can't they just analyze whatever data you collect?
Because a good statistician does much more than just run tests. They can provide invaluable input into the study design itself, helping you refine your research question into something testable, advising on the most appropriate outcome measures, calculating the required sample size correctly, planning the randomization process if needed, and crucially, developing a detailed statistical analysis plan before you collect any data. This ensures that the data you collect can actually be analyzed appropriately and rigorously to answer your primary research question. Trying to fix fundamental design flaws or inappropriate data collection retrospectively through statistical gymnastics is often impossible or leads to very weak conclusions. They should be essential members of your project team right from the start.
Okay, message received. Integrate the statistician early and often. Now, what are some of the basic statistical terms the source mentions for describing or summarizing data?
It lists some of the common descriptive statistics you'll see. The mean, which is a simple arithmetic average, the median, the middle value when all the data points are ranked in order, the mode, the value that occurs most frequently, and the range, which is simply the difference between the largest and smallest values in your dataset. These give you a basic snapshot of your data's central tendency and spread.
And why does the source emphasize the importance of understanding how your data is distributed, whether it's normal or non-parametric?
The shape or distribution of your numerical data is fundamental because it determines which type of statistical tests are appropriate to use for analyzing it. Normally distributed data, often called parametric data, tends to follow a symmetrical bell-shaped curve when plotted. Many common statistical tests assume this normal distribution. If your data isn't normally distributed, it might be skewed, for example, then you typically need to use different types of tests, known as non-parametric tests, which don't rely on that assumption of normality. Using the wrong type of test just because it's familiar or easy is a very common error that can lead to completely invalid conclusions.
So the type of data you have, is it numerical or categorical? And if it's numerical, its distribution, is it normal or not, guides your choice of statistical test. What are some examples of common tests mentioned for different situations?
The source gives a few common examples, but strongly emphasizes again that you really need professional statistical guidance for correct application in your specific study. But for instance, if you have numerical data that is normally distributed and you want to compare the means between two independent groups, like a treatment group and a control group, you might use an unpaired t-test. If you're looking at changes in a normally distributed variable over time within the same group of individuals, like measuring blood pressure before and after a treatment, you might use a paired t-test.
Okay, those are for normal data. What if it's not normally distributed?
If your numerical data is not normally distributed, you'd use the non-parametric equivalence. For comparing two independent groups, that might be the Mann-Whitney U-test, sometimes called the Wilcoxon rank sum test. For comparing changes over time within the same group, the non-parametric equivalent of the paired test, you might use the Wilcoxon signed rank test.
And what about data that isn't numerical at all, but categorical, like comparing the proportion of patients who had a complication between two groups?
For comparing proportions or frequencies in categorical data between two or more groups, the chi-squared test, or Fisher's exact test for small sample sizes, is commonly used.
It's definitely clear why expert statistical help is needed to navigate that. Once the tests are run, how should you interpret the results? The source mentions p-values and confidence intervals.
Yes, and it suggests that confidence intervals, CIs, are arguably the best way to interpret the clinical meaning of results. A 95% confidence interval gives you a range of values within which you can be 95% confident that the true effect or difference in the overall population actually lies. It gives you a sense of the precision of your estimate. If the confidence interval for a difference between two groups includes 0, for example, the CI ranges from -0.5 to +1.5, it usually implies that the finding is not statistically significant at the 5% level because a true difference of 0 is considered a plausible value within that range.
Okay, so the CI gives you the plausible range of the true effect size. What about the p-value then? What does that tell you?
The p-value gives you the probability of observing a result as extreme as, or more extreme than, the one you actually found in your study, if the null hypothesis were actually true, i.e., if there was really no difference or no effect in the population. By convention, a p-value less than 0.05, p.05, is typically taken to indicate a statistically significant result. This means there's less than a 5% or 1 in 20 chance that you would have seen such a result purely due to random sampling variation if there was no real underlying effect.
But the source gives a really crucial caution about relying solely on p-values, doesn't it? About statistical versus clinical significance.
Yes, and this is a key insight for clinicians interpreting research. Statistics fundamentally deal with probability and chance, but as clinicians, we need to think about clinical significance or importance. A study, especially a very large one, might find a statistically significant difference, p 0.05, for a very, very tiny effect size that has absolutely no meaningful impact on patient care or outcomes. The source makes the point that if a study requires highly sophisticated statistical analysis just to find a difference that barely scrapes past the p.05 threshold, then that difference is unlikely to have major clinical significance in practice, even if it meets the statistical definition.
Don't be overly impressed by a low p-value if the actual difference observed is tiny or clinically irrelevant.
Exactly. And the source also warns that if you test enough different variables or outcomes in any given data set, you will eventually find some statistically significant differences purely by chance alone, the multiple comparisons problem. Studies that examine many endpoints require more complex statistical approaches, like multivariable logistic regression, to properly account for this and identify which factors are independently associated with the outcome.
So, the take home message is that clinical results should ideally show clear, meaningful differences that are fairly evident even before you get bogged down in complex statistics. Statistical significance doesn't automatically equal clinical importance.
Precisely. Statistical software packages are incredibly useful tools for performing the calculations, but you, the researcher or reader, need to understand why you're using a particular test, what the assumptions are, and most importantly, what the results actually mean in the real-world clinical context.
That provides a really helpful perspective on interpreting statistics critically. Now, beyond the complexities of doing your own research, the source talks about the equally important skill of analyzing a scientific article written by others.
Yes, this is absolutely fundamental for staying current in your field and practicing genuine evidence-based surgery. While actually doing your own research is probably the best way to truly understand the whole process, warts and all, you absolutely need the skills to critically evaluate the constant flood of published literature that comes across your desk or screen.
What's a good systematic way to approach that critical appraisal? How do you judge the quality of a paper?
The simplest method, the source suggests, is to use a structured checklist designed for evaluating research quality. It specifically highlights the consort statement, Consolidated Standards of Reporting Trials, which was developed internationally to improve the quality and transparency of reporting in randomized controlled trials. Using the consort checklist guides you to systematically evaluate key aspects of how the trial was reported, things like the clarity of the objectives, the details of the randomization and blinding methods used, how the results are presented, including handling of missing data, and whether the discussion appropriately addresses potential sources of bias and considers the study's external validity or generalizability.
So, Concert essentially helps you check if the authors have reported their trial thoroughly and according to recognized best practices, which gives you more confidence in their findings.
Yes, exactly. Looking closely at the study design and methodology as reported is paramount when deciding how much weight or value you should give to a particular trial's conclusions. However, the source also wisely cautions that even a study describing itself as randomized doesn't automatically guarantee it was a high-quality study. The randomization might have been flawed, the blinding inadequate, or the analysis inappropriate. Formal trial quality scoring systems, like the JDAD score, which the text briefly mentions, exist for a more in-depth quantitative assessment of trial quality, although critical appraisal checklists like Consort are often more practical for clinicians.
Are there similar reporting guidelines or checklists for other types of articles, not just RCTs?
Yes, absolutely. The source mentions the PRISMA guidelines, preferred reporting items for systematic reviews and meta-analyses, which serve a similar purpose for evaluating the quality of systematic reviews. And indeed, guidelines and checklists are now available or emerging for many other study types as well, such as observational studies, STROBE, diagnostic accuracy studies, STARD, and qualitative research, CORE-AQ. Journals are increasingly requiring authors to adhere to these relevant reporting standards as a condition of submission and publication. So, becoming familiar with these checklists is invaluable both for planning and reporting your own research rigorously and for critically appraising the work published by others.
Essential tools for both producers and consumers of research. Okay, so once you've successfully completed your own study, analyzed the data, and interpreted the findings, the crucial next step is presenting and publishing it.
This is a vital and sometimes overlooked part of the research process. The source strongly stresses the ethical importance of not leaving your research results unreported and unpublished, even perhaps especially if they are negative or inconclusive findings.
Why is publishing negative results so important?
Because failing to publish studies that don't find a positive effect leads to what's called publication bias. If only the positive studies get published, the overall picture presented in the literature becomes skewed, potentially making interventions seem more effective or less harmful than they truly are. It also leads to wasted effort if other researchers unknowingly repeat studies that have already been done but never reported.
So, even if your study didn't find the dramatic breakthrough you hoped for, reporting it honestly is still a valuable contribution to the scientific record.
Absolutely. The source realistically points out that most studies aren't groundbreaking game changers. Very few surgeons will ever publish truly seminal articles that completely revolutionize practice. But all properly conducted studies, regardless of their outcome, contribute incrementally to the overall body of knowledge, whether by confirming existing findings, refining our understanding, quantifying uncertainty, or importantly, showing that a particular hypothesis was likely incorrect.
Okay, so dissemination is key. How do you decide where to present or publish your findings? Aim high or be realistic?
You need to be strategic. Consider the main message and the likely impact of your study, and then aim for the most appropriate form. Major, well-conducted randomized trials or large national audits with potentially practice-changing implications probably belong at major international scientific meetings and should be submitted to high-impact international peer-reviewed journals. Smaller observational studies, pilot projects, or local audits might be better suited for presentation at regional meetings or publication in more specialized or regional journals. Getting advice from experienced mentors or senior colleagues who know the publishing landscape is incredibly helpful in targeting the right venue.
That makes sense. Match the scope and impact of the study to the audience and reach of the venue. What's the single most important piece of practical advice the source gives for actually getting your work published in a journal?
It's remarkably simple, but often ignored. Follow the journal's instructions for authors accurately. Every journal has detailed guidelines on formatting, structure, word counts, referencing style, etc. Adhering to these meticulously significantly increases your chances of getting past the initial editorial screen and into the peer review process.
Pay attention to the details. What about presenting at scientific meetings? Is that worthwhile?
Definitely. Presenting your work at national or international meetings, even if it's only a poster presentation rather than an oral one, is a great way to disseminate your findings relatively quickly, get valuable feedback from peers and experts in your field, and build your professional network. The source notes that meetings are often quite keen to accept abstracts, especially posters, as it helps boost attendance and showcases the breadth of ongoing work.
Good way to get early feedback. And the formal process for publishing in a peer-reviewed journal involves...
Typically, you submit your manuscript to the journal. The editor first assesses its suitability and quality. If it passes that initial screen, it's sent out for anonymous review by other experts in the field, your peers. Based on their reviews and recommendations, the editor makes a decision: accept, request revisions, major or minor, or reject. Editors can also offer valuable advice on improving the manuscript. The traditional publishing model has the author publish for free, with costs covered by library subscriptions or reader payments. However, the open access model is becoming increasingly common.
How does open access work?
In the open access model, the author, or their institution or funder, pays an article processing charge, ATC, upon acceptance. But the final published article is then made freely available online for anyone in the world to read immediately without needing a subscription. The source suggests this model may well become the standard in the future, as it significantly increases the visibility and potential impact of research findings.
Shifting the cost from the reader to the author funder, but maximizing accessibility. Now, what about the standard structure for writing up a scientific article? Is there a template?
Yes. The source highlights the universally recognized MRAD format: introduction, methods, result, and discussion. It calls this structure inviolable for most original research articles currently, although acknowledges that the flexibility of electronic publishing might lead to changes in the future. But for now, MRAD is king.
Okay, IMRAD. Can you briefly outline what typically goes into each of those sections?
Sure. The introduction should be relatively short and focused. It provides the necessary background context, explains the rationale for the study, why was it needed, and clearly states the specific aims or objectives of the research.
Set the stage, state the purpose. What about methods?
The methods section needs to be detailed and precise. It should describe exactly how the study was designed and conducted, the setting, the patient population, including clear inclusion and exclusion criteria, the interventions performed or exposures measured, the primary and secondary outcome measures and how they were assessed, and the statistical analysis methods used. Crucially, it must identify potential sources of bias and describe the steps taken to minimize them, like randomization or blinding. Any novel techniques should be described in sufficient detail for replication, while standard techniques can often just be referenced.
Provide the full recipe so others can understand and potentially repeat it. Then results.
The results section should present the main findings of the study clearly and objectively, without interpretation or discussion at this stage. The source suggests that results are often best presented using tables and figures for clarity and conciseness. The text should highlight the key findings shown in the tables and figures, but avoid redundantly repeating all the specific data points. It should also report on participant flow, baseline characteristics, and any adverse events.
Just the facts, clearly presented. And finally, the discussion.
The discussion is where you interpret the meaning and significance of your results. Crucially, the source emphasizes you should not simply repeat the introduction or regurgitate the results section here. Instead, you should summarize the main findings briefly, then place them in the context of what was already known from previous research, comparing and contrasting your results. You need to discuss the strength and, importantly, the limitations of your study honestly. You can then suggest implications for clinical practice or policy and propose directions for future research based on your findings. The source wisely warns authors to avoid flights of fantasy or wild imagination. Editors will quickly delete unsupported speculation. Following standard formats for structuring the discussion, like those promoted by journals such as the BMJ, can be helpful.
Interpret, contextualize, discuss limitations, suggest implications, and references.
And yes, finally, the references section must list all the sources cited in the text. They need to be relevant, preferably up-to-date, and formatted precisely according to the specific journal's required style. Accuracy here is essential.
IMRAD, introduction, methods, results, discussion, plus references. Got it. That provides a great framework. Finally, let's try and bring all these threads together by touching on the concept of evidence-based surgery. How does all this fit into that bigger picture?
The Source France Evidence-Based Surgery, or EBS, has a fundamental shift in surgical philosophy and practice. Historically, surgery was often seen more as an art, where different experienced surgeons might legitimately approach the same clinical problem quite differently based on their individual training, experience, or deeply held beliefs, their personal artistry. Evidence-based surgery represents the movement towards systematically using the best available clinical evidence, gathered rigorously from well-conducted studies like the ones we've been discussing, to inform clinical decisions and determine the most effective and safest ways to manage patients.
So it's about moving practice away from being based primarily on individual opinion, anecdote, or tradition towards being guided more by robust collective data.
Exactly. The challenge, historically, as the source points out, is that even when good evidence existed, it wasn't always effectively gathered, synthesized, critically appraised, and disseminated to the surgeons who needed it at the point of care. The source gives the powerful historical example of thrombolysis, clot-busting drugs. For heart attacks, compelling evidence of benefit from multiple trials was actually available for several years before the practice became widely accepted and incorporated into standard guidelines, simply because the evidence hadn't been properly compiled, summarized, and promoted effectively to clinicians.
That's a truly stark illustration of why this whole process of conducting good research and synthesizing and disseminating it effectively really matters for patient outcomes. Where does this accumulated evidence typically get synthesized and stored so clinicians can access it?
Key resources mentioned include organizations like the Cochrane Collaboration. Cochrane is renowned globally for producing high-quality systematic reviews and meta-analyses, which meticulously search for, appraise, and statistically combine the results of multiple individual studies on specific clinical questions. Their database of controlled trials is also an invaluable resource for finding relevant primary studies. Additionally, the websites of major surgical journals often archive important trial data and systematic reviews.
And the underlying idea is that as this body of reliable evidence grows and becomes more accessible,
It should gradually help to smooth out unwarranted variations in clinical practice between different surgeons or institutions. As the optimal approaches for various conditions become clearer based on accumulated evidence, these should ideally be incorporated into clinical guidelines, training programs, and quality standards, leading to more consistent and effective care for all patients.
how is that pooling of evidence from multiple studies often achieved statistically? You mentioned meta-analyses.
Yes, meta-analysis is a specific, complex statistical technique used within many systematic reviews. It allows researchers to quantitatively combine the numerical results from multiple similar individual studies, often RCTs, addressing the same question. By pooling the data in this way, a meta-analysis can produce a single overall summary estimate of the intervention's effect, like an odds ratio or a mean difference that is generally more precise and statistically powerful than the estimate from any single study included in the analysis. They are a very powerful tool for summarizing the overall state of the evidence on a specific treatment or comparison.
So individual audits help us check our current practice. Individual research studies generate new knowledge, and then systematic reviews and meta-analyses synthesize that knowledge. And all of this, when conducted meticulously, reported transparently, and appraised critically, feeds directly into this growing body of evidence that underpins evidence-based surgery, ultimately aiming for better, safer, and more effective patient care.
Precisely. That's the virtuous cycle. Mastering the principles we've dug into today, from asking the right question, designing a robust study, executing it ethically and efficiently, analyzing it correctly, and reporting it honestly, is absolutely fundamental for surgeons not only to contribute to this vital body of evidence, but also to be able to critically appraise and appropriately utilize it in their own daily practice.
Wow, we have gone incredibly deep today. We've journeyed all the way from understanding that critical initial distinction between audit and research, through navigating the structured audit cycle for quality improvement, exploring the power of collaboratives and snapshot audits for generating hypotheses, then meticulously planning a research question, building an effective team, designing the study with careful consideration of different study types, calculating adequate sample size, and tackling bias. We then moved into the practicalities of protocols, data management, leveraging technology, and navigating the complex world of regulatory and ethical approvals. We wrestled with the challenges of statistical analysis and interpretation, developed the crucial skill of critically appraising others' work using tools like Consort, and finally discussed how to effectively present and publish your own findings using the IMRAD structure, ensuring they contribute to the evidence base that defines modern evidence-based surgery.
It really is a comprehensive journey, isn't it? And truly mastering these principles is, as we said at the start, how surgeons move beyond just technical skill to really evaluate their own practice effectively, contribute meaningful new knowledge to the field, and critically appraise the vast amount of literature published each year. It's about operating like the elite, reflective professionals in this field.
Absolutely, and it certainly leaves you, the listener, with a lot to think about. Here's a final thought to take away. Given the clear importance of collaboration in generating robust surgical evidence and the continuous need for high-quality research to improve patient care, what specific role will you play in contributing to, critically appraising, or perhaps even leading efforts to improve surgical evidence within your own career path or sphere of influence?
Or maybe turn it slightly differently. How can the surgical community as a whole work better together to ensure that the evidence being generated isn't just high quality from a methodological perspective, but is also relevant to patient needs, and perhaps most importantly, is effectively and rapidly translated into tangible changes in actual patient care at the bedside, closing that gap between research and practice? Something important to chew on.